Today's topic is EMWP-13. That is the title of the topic, or the main topic is the electromagnetic wave propagation, and the today's title of the topic is boundary conditions for the fields B, H, D and E. That is the magnetic field B, magnetic field intensity H, the displacement field vector, electric displacement field vector D, and electric field intensity E field vectors across the interface of the two non-conducting media. So here in this topic, what we will be discussing the propagation of the wave. When electromagnetic wave propagates from one medium to another, and which boundary conditions are necessary for the continuity of those field vectors, that is like B field vector, H field vector, D field vector and E field vector. So the continuity, so that there is no discontinuity when they move from one medium to another. So we will be looking at that perspective. Now the boundary conditions we take first, for the B field vector, we take the normal component of B in this case. What you can see here, we have drawn a figure where there are two media, medium 1 and medium 2. Both are we are considering medium 1 to medium 2 with the permeabilities mu1 and mu2. The Gaussian surface, that is the cylindrical surface, is drawn. Now this cylinder is actually basically pillbox. It is not exact cylinder, still its height is shown pretty large, but in actual we take a pill, like a medicine pill, we have tablet or pill whose height is smaller than the radius of this circular surface, this circular area, or the radius of this circular surface area. So this very small height is very this is the height is small and the surface area is larger than the height, that is the radius is larger than the height. So the we have now taken the B1 field vector in the medium 1, B2 field vector in the medium 2. There are the N1 unit vector normal and N2 unit vector normal in the respective media 1 and 2. Here we will see that the N1 unit vector normal is equal to N2 unit vector normal, with the only change is the polarity in opposite direction. Otherwise they are same in magnitude. Okay, so this there are, we can see that this pillbox has the three surfaces, S1 and S2. We should have given, but anyway this doesn't make any difference. This S1 S2 is not related with the medium, but they're related with the surface. So we could have, let me correct, okay, I just made the correction. This now let's say the S2 is the surface of this Gaussian surface pillbox cylinder in the medium 2 and S1 in the medium 1. S3 is we take the surface all around and is very has a negligible surface area. Now we have given all these the same description in this note, that we consider that the magnetic field vector B1 incident on the interface of the two media 1 and 2, with the respective probabilities B1 and mu2. Let B2 be the magnetic field vector in the medium 2, while N1 and N2 are the normal unit vectors of the medium 1 and medium 2 respectively, as shown in the figure. So let us now consider that small pillbox which I have already described. We can read out that thing. Now we pick the pillbox cylindrical surface to apply the Gauss's law of flux. So Gauss's law for magnetic flux is given as the surface integral B dot n dA, which is equal to 0. This is equation number 1. Since the Gaussian surface consists of two main surfaces S1 and S2, hence the magnetic flux through the surfaces across interface is expressed as the surface S1 integrated over the whole B1 dot N1 dA1 plus surface S2 integral of the surface integral of the S2 over the S2 B2 dot N2 unit vector dA2, which is equal to 0. Since B1 we consider one particular instance is constant, B1 is not changing, B2 is not changing, and similarly N1 and 2 are also constant, they are not changing. Only changing thing is the area element, which we took a small area element on that big surface, that is S1 or S2. So we take the integral inside. So what we get, the surface integral of the dA1 will give you the total surface area of that cylindrical surface, and similarly dA2 or S2. And what we have, since this is the uniform cylinder pillbox, so S1 is equal to S2 is equal to S. So putting those values here, and also we have the N1, and N1 is equal to minus N2, which is equal to minus N. N1 is equal to N, N2 is equal to minus N. So what we have, that the normal unit vectors we can put over here. So this should be the negative sign in a moment. So here we have B1N minus 2N, because here N1 is equal to minus N2, which is equal to minus N. So B1N minus B2N is equal to 0, or B1N is equal to B2N, which shows that the normal component of the B is continuous across the media, medium 1 and medium 2. So the continuity is shown that exists. So now we take the tangential component of H, magnetic field intensity H. The relationship for the magnetic field intensity H may be expressed in terms of the Ampere's law, which is the loop integral, the closed path integral H dot dl is equal to I, which is the current. We take the equation number 1, and let us now draw now for the checking the condition for the magnetic field intensity H. We take the same interface, forward interface SS prime. We draw a rectangular loop or path ABCD. ABCDA, this path is drawn, which has the total length delta L. Only we take the difference is that this is in the opposite direction. We draw the, obviously the path is from A to B and B to C, C to D and D to A. We call that, in the medium 1 it is having the field vector H1, and DL1 is a small length element we take in that particular the medium length element, and DL2 in the medium 2. H1 is the field vector field intensity, magnetic field intensity in medium 1, and H2 in the medium 2. So delta 2 and delta L, this whole is delta L, are the same, equal to delta L2 and delta L1 are the same. Delta L is equal to delta L2 is equal to delta L, but only the difference is there, they are in opposite directions, but anyway they have the same length if we measure the length from A to B or C to D. N1 and N2 are again the same unit vector normals. Now what we have, we consider this closed path ABCD across this the segment AB and CD are the large as compared to the AD and BC. Again we take the thickness of the height of this loop is very small as compared to the segments A, B and CD. So what we have, the segments A, B is equal to delta L1 and CD is equal to delta L2, while DL1 and the DL1 and DL2 are the small length elements of the segments delta L1 and delta L2 respectively, as shown in the figure. We have already shown that the small length elements we are taking. This is a small length element, and this is also a small length element. So the applying now Ampere's orbital law to the loop, which gives us the loop integral h dot dl is equal to the loop integral which is the over the length dl1 h1 dot dl1 plus h2 dot dl2. Since the tangential component of the h1 of the h1 is h1t is along the dl1. Okay, so here what we see that, let me give you, if we take this tangential component, this is the normal component, this is a h2, and if you take the this projection and we draw here, this one is the h2t and this one is the h1t. So these are the tangential components which are parallel to the dl1 and dl2. dl1, this is dl2, h2t is also along the dl2, and similarly there is the h1t, and here is the dl1 is also both are parallel. So in this case, in one case, we have the h1t loop integral dl1 minus h2t over the loop integral dl2. So one is the opposite, one is the parallel, the other one is the anti-parallel. So what we take and the integral applies to the variable length element, which is dl1, h1 and h1t and h2t are not varying. So we take the delta L1 minus h2 delta L2. So dot product, since they have making either 0 or 180 degrees, so that comes to the cosine of theta 0. Cosine 0 is 1. So we get the dot product vanishes in terms of we get the h1t and the L1 h2t and dl2 with the negative sign. So since delta L1 is equal to delta L2 is equal to delta L, so that delta L we can take common, and if we consider the I to be the interface having a zero or free charges, having zero free charges, that I is equal to 0, in that case we can cancel out delta L. So we can say that the tangential component h1t is equal to h2t, that is tangential component h will be continuous, but if the interface contains free charges, then the h1t minus h2t will be equal to I over delta L. There will be discontinuity by this factor. h1t will be equal to I over delta L plus h2t. h1, this factor is also, since it's a vector quantity, and the current density when we take J is also a vector quantity, then we can describe the this h1t minus h2t as the n unit vector normal cross the plane of these two, the unit vector normal the cross the h1t minus h2t, that will describe this this side in the vector form. Okay, that will be equal to current density J. J will be also the perpendicular to the surface direction, so that will be there. Now we consider the third case, which is the normal component of electric displacement D. Let us now consider again the this figure having the two media, which is medium 1 and medium 2. Medium 1 and medium 2, d1 is the displacement field vector in the medium 1, d2 is a displacement field vector in the medium 2. H is the height, and again the S1 is the surface area of the spill box. The S2 is the surface area in the medium 2, S1 is the surface area in the medium 1. N1 and N2 are the unit vector normals. Epsilon 1 and epsilon 2 are the permittivities of the both media. So the let us consider now the d1 field vector incident at the interface of the two media, medium 1 and medium 2. d1 be in the medium 1 while d2 field vector propagates in the medium 2. Let epsilon 1 and epsilon 2 be the permittivities of medium 1 and medium 2 respectively, as shown in the figure. So let S1, SB, S2 be the surfaces of the pillbox, the surface areas on the interface with a negligible height h. Let N1 and N2 be the two normal unit vectors in the medium 1 and medium 2 respectively. From Maxwell's first equation in the integral form, we have the divergence of d when integrated over the whole volume. Volume integral of divergence of d dv is equal to the volume integral the rho dv, which is the volume charge density. Applying Gauss's divergence theorem to the equation 1, where we have defined this rho as a volume charge density, what we get that the volume integral, we move from the volume integral to the surface integral d dot n dA, which is equal to now the volume charge density moves from the volume to the surface, which is sigma dA over the surface integral, where sigma is the surface charge density. So applying surface integral to the respective surfaces S1 d1 dot n1 dA minus we can call it dA1 dA2, but both are, you will see at the end, will be the same. Then we have the so which is the d1 dot n1 dA1, we take a small area element on the surface 1 minus S2 d2 dot, we take the actually n1 is equal to minus n2 in this case. So we can put either that n1 is equal to n2 is equal to n, the common unit vector normal as well. But anyway, so we have they are opposite in direction, so we put a minus over here. So the d2 dot n2 dA2 is equal to sigma surface integral over the whole surface dA, both total surfaces we take the surface charges, the upper surface and the lower surface. We neglect the surface 3 because of the negligible size. Okay, so what we have now, the over here, that the medium, we take the surface integrals to dA1 and dA2 because they are the changing variable parts, while the d1 is constant and n1 is constant. So we, if we integrate the surface S1 over the whole surface S1 over the whole dA1, we get S1, similarly in this case S2, and the surface over the whole dA, which is total surface of both S1 plus S2. So what we have now, d1 dot n1 into S minus d2 dot n2 unit vector into again S is equal to sigma S. S is cancel out, so d1 n minus d2 n is equal to sigma. Equation number 3. If now the surface charge density at the interface is equal to 0, then we have the d1n minus d2n is equal to 0, or d1n is equal to d2n. This equation 4 shows that the normal component of the displacement field vector is constant, is continuous across the boundary. Now if sigma is not 0, there might be a chance that it could be a dielectric which is polarized at the interface, or it is having free charges. Then the normal component of D is not continuous across interface. We have the equation of continuity. For the continuity, the divergence of J is equal to negative rate of change of the volume charge density. So integrating this equation, and then we gave it the equation number 5, both sides of equation over the volume V, what we get, the in this case we will be over the volume dV is equal to minus delta by delta t. We integrate the over the volume V, the volume charge density rho. So applying the divergence theorem to the left hand side, this one, we get the J dot N dA is equal to minus negative, or the negative rate of change with respect to time or surface integral sigma dA. So what we have, the now taking the surfaces in case of that individual surfaces. So we have the J integrating the current density J1 dot N1 dA1 similarly minus S1 S2. So J1 dot N1 dA1 minus S2 J2 dot N2 dA2, where N1 N2 is negative opposite to the N1. So further we take again the integral inside to the dA1 and dA2, so that they are equal to respective surfaces S1 and S2 surface area, and the dA, the total surface area on the both side, is equal to S. So J1 dot N1 S minus J2 dot N2 S we get from this side. So putting that into the equation, what we get, J1 N S minus J2 N S is equal to delta sigma by delta T into S. S is cancelled out, we are left with the J1 N minus J2 N is equal to negative rate of change of the surface charge density. Now if monochromatic radiation is considered, then the surface charge density varies as e raised to minus j omega t. So sigma is equal to sigma naught, which is the maximum value of the charge density, which is times the e raised to minus j omega t. So integrating differentiating this sigma with respect to t, we get minus j omega sigma naught e raised to minus j omega t, or this is whole term is again sigma minus j omega t, that is the delta by delta t of sigma is equal to minus j omega sigma. So we have now equation of Ohm's law in terms of the field equation. We have current density J is equal to G times E, where G is the conductivity, this is the current density, and this is the electric field intensity. So putting the values in the above equation, in the last equation 8, so G1 E1 N minus G2 E2 N is equal to, since there is a negative rate, was there, the minus cancel out, J omega sigma. So what we have, the from equation 3, D1N is equal minus D2N is equal to sigma. Putting that also here in equation 10, we get G1 E1N minus G2 E2N is equal to J omega D1N minus D2N. Or we have after rearranging the above equations, we can rewrite the final equation that E1N into G1 minus J omega epsilon 1 is equal to E2N into G minus J omega epsilon 2 epsilon 2. So this equation shows that the discontinuity of the normal component of E, or similarly we can say the E is discontinuous, so as the D as well, if we just simply multiply with respect to the epsilon 1. So the normal component is discontinuous in case there is a surface charge density or free charges at the interface. So with this we reach to the end of the topic. We will meet inshallah again in the next topic with a new topic. Thank you.